Let's start out by refreshing everyone's memory on the things you all totally know by now and just ace your test on. Right? Hopefully. We've talked a little bit about the octet rule already. Noble gases are stable because they have a full valence shell, the outer energy level of electrons. In ionic bonding, neutral atoms gain or lose electrons in order to give themselves a complete outer shell. For most elements, this means 8, while hydrogen and helium can only fit 2 into their small first energy levels. Ionic bonding is when one element does what? It transfers one or more electrons to another element. In this picture, the metal sodium transfers its one valence electron to chlorine, making a positive sodium ion and a negative chlorine ion, with their opposite charges then attracting each other to form an ionic bond. Just remember this only happens that the ions can have the same kind of electron configuration with a full outer shell as a neutral atom of a noble gas. This is like the Pretenders video, or this small dog that was painted to look like a panda by a seedy traveling circus in China. I made sure I showed you this at the very end of the last section of ionic bonding, but it doesn't apply anymore. You need to know that ionic bonding involves the transfer of electrons, but we're moving on now to the next section with a different look and a different verb. Last week we saw how ionic bonds form because one element, a metal like sodium, has a much weaker attraction for electrons, the electronegativity, than a non-metal like chlorine, which has a strong electronegativity. The difference in electronegativities will be at least 1.7 in these situations. When electrons are transferred from one to the other, everyone achieves a full valence shell to fulfill the octet rule and everyone's happy. But what about cases like these very common molecules, water H2O, carbon dioxide CO2, and oxygen gas O2? These electronegativities are much closer to each other. The differences are all under 1.7, and in the case of oxygen gas, O2, the difference is actually 0 since it's just two atoms of the same element. So in these cases, who transfers their electrons? Who's going to give up their electrons? Who doesn't want their electrons? Well, in covalent bonding, the truth is that everyone wants their electrons. So where do we go from here then? What do these words mean? Coexist, cooperate, copilot? If coexist is existing together, cooperate is working or operating together, and copilot is two pilots flying together, what does that prefix co refer to then? It sure seems like it means something being or happening at the same time or together. Now think what you know about the word valence. If valence electrons are those in the outermost energy level, the outer ring, then putting it all together, covalence or covalent, probably going to involve electrons being in the outer rings together at the same time. Covalent bonding, which you may see called molecular bonding at times, depends where you're seeing questions from, is different from ionic bonding in that atoms will share electrons rather than transfer them. Let's repeat that again. For ionic bonding, the key verb was transfer. For covalent bonding, the key word to look for that you always want to associate with this type of bonding is share. No, something's wrong here. There we go. Share. Share the electrons. Ionic bonds were able to transfer electrons because the compounds were made from metals and nonmetals. But covalent things are made entirely of nonmetals. And since every one of the nonmetal atoms is really close to getting to 8 valence electrons, none of the atoms wants to be the one to give theirs up. So instead they have to work together and share what they have. Covalent bonding is the high school science version of the peace and unity message in every alien invasion movie. We can only get through this together. We're not doing any drawing of covalent compounds today. We'll do that later in the chapter. But let's look at a few quick characteristics that differentiate the ionic compounds we've already learned about from the covalent or molecular compounds we'll spend the next week or so diving into. As already seen, ionic compounds were metal and nonmetal, or one of those two with the polyatomic ion, and the elements had a large difference in electronegativity values. In covalent bonding, the compound is made up of entirely nonmetal atoms that are very similar to each other. So there's a much smaller difference in electronegativities if one exists at all. It could be 0. This leads to electrons being transferred to allow for ionic bonding, but being shared by atoms that form covalent bonds. One more time, ionic bonding transfers electrons, and covalent bonding shares electrons. Just get used to saying that over and over again. One of the physical properties of ionic compounds was that they were hard, solid substances, and I told you to remember them as chunks of salt crystals. Just think of that example, because salt is NaCl, metal and nonmetal. I think it's a really easy thing to remember like that. Covalent substances, in contrast, can be solids, liquids, or gases, and they're soft. We know that ionic compounds require high temperatures to make them melt or boil, while covalent compounds have low melting and boiling points. Ionic compounds are really bad conductors of heat and electricity when they're solids, but much better conductors when they're liquids or dissolved in water. Covalent compounds are always bad conductors no matter what phase they're in, but this also means that they're really good insulators and can hold in heat or charges. So things we use to protect ourselves from heat or electricity are covalent compounds. One more time, if we compare electronegativity numbers for different elements, we can tell what type of bonding is taking place, with the number 1.7 being our signpost for comparisons. Ionic bonding is when the difference in the electronegativity values is greater than 1.7, so then obviously for covalent bonding, the difference will be less than 1.7. This will be especially evident in cases like the oxygen gas molecule we saw a couple slides ago, O2, which has two atoms of the exact same element attached to each other. I'm just going to leave this right here to be appreciated. I don't know if this was actually put out by General Electric or if it's parody, but this is fantastic regardless. We watched the first part of this in class the other day, and we'll keep coming back to it as we learn new pieces of the bonding puzzle. Yeah, you wouldn't, would you, chemistry cat? Finish your notes in the form, and we'll start seeing how this works when next we meet.